Hey everyone. We did a video earlier called Measurement and Uncertainty, and in that one I discussed the reasons that all numbers are uncertain. We showed you how you can determine the uncertainty in those individual digits. The big rule was basically the last digit to the right is the uncertain digit. You can only have one uncertain digit. I then came up with some significant digit rules and showed you how to use those. But I thought I'd put it all together in a document and make that available to anyone that wants it, and also go over it and some examples along with it, and mention a couple other things about significant digit rules. For instance, last time I did mention that significant digit rules are not the be-all and end-all. In fact, they're actually prone to error. So I'll give you a couple examples where you'll see that error can come in and you end up having to adjust your results. Not all instructors are so particular about it. If you're following the significant digit rules, a lot of teachers are happy, but the problem is there are instances where the significant digit rules fail you. And as I said before, you'll learn in more advanced classes ways to deal with what we call error propagation. So let's get started by first sharing my screen. So here's a document that I put together specifically so we can so you can see it in writing, other than my handwriting, of course. If you guys are interested in actually getting a copy of this, all you have to do is, let's see, ooh, did not mean to do that, is send an email to billy@physicssolutions.com. That's PHYSICS SOLUTIONS.com. That's billy@physicssolutions.com. Just send me an email and I can send you that document if you'd like a copy of it. Now back to sharing the screen. So here's the document. Basically what we discovered was a neat way in which you can determine whether a number is a significant digit or not, and introduced a new term. We call them significant digits, or we also call them significant figures, or SigFigs for short. So you can see right here, it says we call the leftmost non-zero digit in a number the most significant digit, or MSD. If a decimal is present in the number, then the rightmost digit, period, is called the least significant digit, or the LSD. If a decimal symbol is not present in the number, the rightmost non-zero digit is the LSD. And then finally, the rule is that the MSD, the LSD, and everything in between those are significant digits. So you can see, for instance, in the number 1500, the MSD is the 1, the LSD is the 5. Because there's no decimal present, these zeros do not matter. You can also see that in this example, 1500.0, the MSD is in fact the 1 again, but this time, since there's decimal present, the very last 0 is the LSD. So that's a few useful examples. Of course, the document has a lot of them on there. There is a rule, though. Generally speaking, instructors will not take the time to write this type of number. They'll more likely, or I say instructors, authors will often just write this number. The problem with this number is that, according to our significant digit rules, it only has 2 sig figs. Whereas a textbook assigns this problem and says 1500 or 500 or something like that, they actually assume, if they wrote 1500, that that'll have 4 sig figs, as if it had a decimal right there. All of that could be taken care of just by using scientific notation. So if you always put it as a number between 1 and 10, where it can be as small as 1, but not as big as 10, and you include the decimal in there, then you'll automatically have the significant digits dealt with, because every digit is going to be significant in that case, except for, of course, these guys. So you can probably see the problem with that. It's a lot more of a pain in the butt for an author to write this number over and over again, and it looks ugly and all sorts of good stuff. So that's the big deal. With each person, whatever class you're taking, you need to find out from your instructor what the deal is on numbers like 1500, 500, 1000, stuff like that. This is where I explain that. Now, using uncertain numbers in calculations, we mentioned this before. Basically, whenever you have a number, that number is going to have the last digit being slightly uncertain. when you multiply two numbers that have an uncertainty, then you got to figure out where that uncertainty lies in the end. And the rules that we came up with are that when you multiply or divide two numbers, the result of the operation should have the same number of SigFigs as the factor, the number being multiplied, the dividend, the number being divided, or divisor, the number being divided into the dividend, with the fewest SigFigs. So in other words, all the players in your mathematical problem, whether it be multiplication or division, you look at all of those numbers that are playing in that, and when they're you find the one with the least number of SigFigs, and that's the one that dictates the number of SigFigs your answer has. You basically find the one with the least number of SigFigs, and you make that the number of SigFigs your answer will have. When taking a sine, a cosine, a log of an uncertain number, or when using an uncertain number as an exponent, it's common to round the result to the number of SigFigs that the uncertain number had. So whatever the first number was, that's what you're going to use. When adding or subtracting, your result should be rounded to match the precision of the add-in, which is the numbers being added, the minuend, the number being subtracted from, and the subtrahend, the number being the number subtracted from the minuend. So again, this is just the players in the addition and subtraction. Basically, you look at which one has the fewest number of decimal places, and then that decimal place dictates where you round your answer to. When performing multi-step calculations, you should keep one or more digits beyond the proper round-off place until the final step. Perhaps tracing them by underlining them, stuff like that usually helps. And then round off or truncate the number at the end. When rounding off a number, you look at the digit to the right of the place where you need to round off. And if that digit is less than 5, you truncate the number, just erase everything after it. Or if that number is 5 or larger, the general rule is you round it up. The problem is that's just a little bit wishy-washy on the number 5. 5 is dead center between them, so it's not necessarily statistically the right thing to do that way. So some instructors go an extra step, which I'll show you later. But the key point is to know that what your instructor does is what you need to do, or what your instructor tells you to do. So most teachers I know of will just have you round off if the number is 1, 0, 1, 2, 3, or 4. And if it's 5, 6, 7, 8, 9, or 10, you're going to round it up. In other words, add one digit to the one that you're rounding, the space that you're rounding at. So some examples of that are, here's multiplying. I wanted you to also see how the units work. So 3.2 times 7.16 times 4.0000. Obviously, this number only has 2 SigFigs, but when I multiply all those, I get all these digits, and notice meters times meters times meters is meters cubed. So when I put the decimal where it's supposed to be, then I realized, okay, well, I got to round this off to 2 SigFigs, so it's going to have to be 92. When I divide, the same process. This time I got 4 SigFigs and I got 2, so I'm going to have to round the answer to 2. Notice in this case, I'm dividing meters by seconds, so the result comes out meters per second. So the answer is 0.74 meters per second. When I add numbers, notice they all have to have the same unit. Notice all these have the units of joules. And this number actually has 5 decimal places. This one has 1 decimal place, and this one has 1 decimal place, which means we have to round the answer to 1 decimal place. So when I add them all, obviously I get 5 decimal places, but only one of them can be used. And since this is where I need to round it to, and this number is less than 5, I'm automatically going to call that what it is, which means I'm going to truncate the number or erase everything after it. So it's 944.0 joules. If you subtract 2 numbers, it's the same rule as adding. 980.51 centimeters per second squared minus 980.1 centimeters per second squared. Notice this one has 2 decimal places. This one only has 1. So I'm going to have to round it to 1 decimal place. The answer is actually 0.41 centimeters per second squared, but once I've rounded that, that's 0.4 centimeters per second squared. Notice again, the units matched when we subtracted. Whenever you add or subtract, the units must match. Here's 725.78 newtons times 6.42 meters. I get 4,659.51 newton meters, which this having the least number of SigFigs, 3 digits, means I should be rounding this number to 3 SigFigs. Notice technically by our SigFig rules, 4660 is 3 SigFigs, but to remove any ambiguity, you should write 4.66 times 10 to the third Newton meters. And finally, 725.78 newtons plus 6.42 meters. You can't do that. They don't have the same units, so you can't add them or subtract them. So here's the special rule that some instructors use. Basically, when you go to round, that 5 is playing too important of a role, and it's dead center, and it shouldn't be automatically rounded up if it's 5 or rounded down if it's below 5. So what they do to account for that is if the number to the right of the round off place is greater than 5, or if it is 5 with any non-zero digits to its right, then we're going to automatically round up. So 7.36 2.736, 2.737, 2.739, 0012, 2.735, 00001 all become 2.74. That makes sense because the number 5 is not just the number 5, it's 5 with a bunch of stuff after it, or it's it's larger than 5. That's the key thing. So that's why you're rounding up. If the digit following the round off place is 5 and no other digits beyond the 5 exist, we round down, just erase the 5 if the preceding digit is even, and round up if the preceding digit is odd. So just it puts that extra randomness in it by whether the preceding digit is odd or even. We're going to round up or round down. So 8.725, notice the 2 is actually even. So we're going to round down. In this case, it'd be 8.72. 2.735, the 3 is odd. So in this case, we're going to round up. So it'd be 2.7, or excuse me. Yeah, it's supposed to be 2.74, not 8.74. So there's some more examples here. As I told you before, significant digit rules are not always accurate. Really, what you're supposed to pay attention to is something called the fractional error. So if you take a number like, let's say this one, 8.725, that has an uncertainty that you assume is at least as big as 1 in this last digit. Well, actually, since we're going to round it off, let's take this one. So let's assume 8.72 has an uncertainty of at least 1 in this last digit. So the fractional uncertainty of this number would be 0.01, which would be the uncertainty, divided by the actual number, divided by 8.72. So 0.01 divided by 8.72 is the fractional uncertainty of this number. What's supposed to happen when you add numbers, multiply numbers, divide numbers, that sort of thing, or even take a trig function of a number, the number that you put in should have roughly the same order of magnitude of fractional uncertainty as the result once you round it off. Okay, you definitely can't make the uncertainty a lot smaller, nor would it be wise for you to make it a lot bigger, because then you're wasting some of the information you do know. So how do we deal with that? Well, you're always supposed to check the uncertainty, the fractional uncertainty in each number. So for instance, 1.09 meters times 0.99 meters squared gives me 1.0791 cubic meters, which by the SigFig rules, notice should only be 2 SigFigs. That's 1.1 cubic meters. However, 0.01 divided by 1.09 is 0.009, which is about 1%. 0.01 divided by 0.99 is also about 1%, but 0.1 divided by 1.1 is actually almost 10%. So that's not acceptable. That's a place where SigFig rules screwed us up. So we try to add the extra digit, in which case it becomes 1.08. So when we look at the fractional uncertainty of 1.08, you do 0.01 divided by 1.08 and you get 0.009, which is about 1%. So this is the correct answer. If you do the sine of 87.9 degrees, you get 0.999328. And according to our SigFig rules, I put in 3 SigFigs. I should round it to 3 SigFigs. So I'm going to call that answer 0.999. However, the fractional uncertainty of the input number was 0.1%. The fractional uncertainty of the output number, 0.001, divided by 0.999, gives me also about 0.1%, so the significant digit rules work fine. If you do the sine of 8.2 degrees, you get 0.142629. Again, this is 2 sig figs though, so we should round that off to 0.14. If I do that, then the fractional uncertainty of the input is about 1%, and the fractional uncertainty of the output, which is 0.01 divided by 0.14, is nearly 10%. So it's really not a very good match, in which case we add another digit and it becomes 0.142, or excuse me, 0.143. So 0.143 has a fractional uncertainty of 0.001 divided by 0.143, which is in fact more like 1%, which is what we have it for. So that's basically it. I just wanted to talk to you about how to deal with significant digit rules a little more robustly, give you a physical document that has the rules, have it actually typed out for you as well, as opposed to reading in my handwriting. So I hope that helps. I'm going to stop sharing my screen and change my video. So again, just email me at billy@physicssolutions.com if you want a copy of this document. I'll send it to you in a PDF form, not in the Word form. Have a good day.